Now I'm going to ask Koji Sakai to start the Sustainability Forum. I should have introduced myself originally, and I apologize for that. My name is Julie Buffenbarger. I am chairman of ACI 130, the Sustainability of Concrete at ACI, and my job and role professionally is with Lafarge as a construction specialist.
Thank you, Julie. Good afternoon, ladies and gentlemen. Welcome to the ACI Concrete Sustainability Forum 6. Firstly, I would like to introduce of this forum. In the past, we have had 5 forums as shown here from the St. Louis, 2008, and after that New Orleans, 2009, Pittsburgh, Cincinnati, Toronto last year. Last forum was the 5th anniversary of this forum. So it means that this time will be 6th forum. As you can see that the topics of the forum, 5th last year, we had 5 speaker sessions. Here that one is the sustainability in the ACI 318 structural concrete building code, which were presented Lando Houston, who was the chair of the ACI 318. And also we had Doug Fulton, Professor Doug Fulton from Canada, University of Toronto. He talked about improving concrete sustainability while designing and specifying for durability. And then we had Michael Collins, Professor Michael Collins, at the same university as the Doug Fulton. He talked about improving the resilience of critical infrastructure. And then we had the Michael Mortimer, who came from Canada again. He talked about the adapting built civil infrastructure in Canada to the impact of the climate change, the codes and standard. And finally, I talked about the what does concrete sustainability mean. Then we had some conclusion from this speech. The first one was the addition of the sustainability in the 318 building code. They decided to include the sustainability in the building code. He mentioned that, was to mention that it is a start to embrace the spirit of sustainability in ACI. And then Fulton concluded that the performance specification can include the chances of obtaining durability. And Michael Collins concluded that robust wind and earthquake dumping systems are needed to enable a new generation of more efficient and resilient designs. We have been designing the columns of the buildings by considering the confinement, but after many years, years that he concluded it is not enough, that we need more different systems, like that dumping systems. This was a very interesting conclusion. And Michael concluded that we must adapt to climate change, and standards are playing a key role in that process. And then finally, I mentioned that without robust infrastructure, homes, and commercial buildings, human society has no chance of meeting the goals of the sustainability. Those are the conclusion of the last forum in Canada. If you summarize the conclusions of Forum 5th, we can say that the next step will be certainly actions to realize the balance of safety, durability, and resilience with environmental stewardship. So the balance of those elements are very important for sustainability. And because of that, this may require us to broaden our outlook and refocus on the challenges with a new lens. The themes of the Forum 6 is sustainable cement and concrete technologies and service life design, how to apply that in EPD, and standardizations. So today we have the two parts. The part one is the presentation by 7 speakers. The first speaker is me. The title is A New Approach for Development of Low Carbon High Performance Concrete. And then we have the Dr. Higuchi, who from Japan is going to talk about the development of a new ecological concrete with carbon dioxide emissions below 0. And then we have the third speaker. Dr. Barcelo from the Lafarge Cement Company. The title of his talk is A Path Towards More Sustainable Cement Manufacturing. And then we have the Professor Harald Muir from Germany. The topics of his talks is the sustainable concrete structures through service life design and eco-efficient concrete. And we have the Dr. Noguchi from the University of Tokyo, Japan. He's going to talk about the ISO standardization on environmental issues for concrete sector. We are now developing ISO standardization on environmental issues for concrete sector. And then our colleague Julie will talk about what are PCLs and EPDs. Nowadays, the EPDs, the importance of the EPDs is greatly increasing, so he will introduce the essence of the current trend. And finally, we have the Professor Dong-Wook Choi from Korea. He's going to talk about recent advances in standardization on sustainability in Korea. Korea is one of the one country which is the very active in the developing of the environmental standards. And then after that, we have the part 2 panel discussions. So I'm going to chair the panel discussion and all speakers, and also the people from floor. We can have the free discussion about some topics. And finally, Julie will wrap up our forum. So please enjoy this forum. Now, I would like to introduce, present my topics. So today's my topics is a new approach for development of low carbon, high performance concrete. As you may know that on September 27th, IPCC fifth assessment report, working group 1, which is the physical science report, announced their latest report. According to that report, the warming of the climate system is unequivocal, and since the 1950s, many of the observed changes are unprecedented over decades to millennium. The atmosphere and ocean have warmed. The amount of the snow and ice have diminished. Sea levels are rising, and the concentrations of greenhouse gases have increased. So it means that we are required to reduce the greenhouse gas, such as carbon dioxide. So the concrete industry is no exception. If you look at the methodology for low carbon concrete, what methodology do we have? One is the efficiency and the innovation in cement manufacture. A good example is a project. I'm very interested in hearing that topics today from Lafarge, and also the use of the supplemental cementitious material is most strong tools. And then reduction of the cement by utilizing superplasticizer, and also if you utilize high-performance concrete, we may be able to reduce the carbon dioxide. But the most efficient method for drastic reduction of carbon dioxide is to replace the cement with a large amount of supplementary cementitious materials. A typical one is the blast furnace slag, which is very low carbon. And in Japan, more than 10 years ago, 15 years ago, 80% carbon dioxide reduction cement was developed and used in a big project, which is the Akashi Kaikyo Bridge in 1998. This bridge is the world's longest suspension bridge. The main span is almost 2 kilometers, 2,000 meters, and the total of the length of the bridge is the 4,000 meters. There is a two bases for the towers. This is that. And we developed in the low heat Portland cement for this which is a tower foundation, as shown here. You can see the people here. It's very small. So how huge the tower foundation is, you can realize that. So we introduced the low heat Portland cement. And there are many developed cement concrete as shown here, from number 1 to number 12. Number 12 is the ordinary Portland cement, and number 10 and number 11 this cement was applied for the foundation of this bridge. And this is the carbon dioxide emissions, quite low. And this is the compressive strength. It's lower than the ordinary Portland cement concrete, of course. And then this is the adiabatic temperature rise. It's quite low compared with that. And okay, this is the fundamental property of this developed cement concrete. And we gather lists from the Akashi Kaikyo Bridge low carbon concrete. The one is the carbon dioxide emission were approximately 50 to 70 kilograms per cubic meter, very low. And adiabatic temperature rises were approximately 20 to 25 degrees Celsius. This was also very low. However, we got many cracks with the width of the 0.45 to 0.5 millimeter in 3 to 5 meter interval. This was due to the increase of the homogeneous shrinkage, which was caused of the blast furnace slag with high specific surface, 6,000 square centimeter per gram. So if you summarize the blast furnace slag concrete weak point, one is the large homogeneous shrinkage, one is low crack resistance, and smaller strength development, and large influence of the temperature and curing condition on strength development, and low resistance to carbonation. You can increase the carbon dioxide emission drastically by utilizing this kind of concrete, but we have the weak point as written here. As a result, we can say that we need to consider the resistance to crack in development of concrete. This is the point why we decided to develop the new concrete. There is the information that change in the compressive strength of cement in Japan. So the gradually increased. That was a bit a change, but the test method was changed here. But you can focus on the strength, compressive strength increasing year by year. And also grain specific surface area of the cement. This is the Puton blast furnace size, and it's quite high, 4,000 right now. And then this is the ordinary Puton cement. Even in ordinary Puton cement, the fineness is increasing compared with the 1970. This is because that the people think that we need to have the early strength development. And earlier temperature rise and low heat Puton cement is quite low, but even if you utilize Puton blast furnace like cement type B, it's quite large temperature. So it means that the possibility of cracking is increasing. And this is the data of the homogeneous shrinkage. This is a ordinary Puton cement. This is the Puton blast furnace cement. It's quite obvious. Depending on the kind of the cement or condition, it's different value, but it's quite obvious. The homogeneous shrinkage of the blast furnace Puton cement is larger than the ordinary Puton cement. So that it means that if you utilize this kind of the cement, you have the possibility to have the cracks. And this is simple data and the situation of Japan. The most of the more than almost 70% of the cement is Puton cement, ordinary Puton. And the blast furnace cement, 23 or 4%. And the other is the highly strength Puton cement. So still we have the much of the ordinary Puton cement. This is a situation. I don't know the situation in the United States, but this is a situation in Japan. So it means that we have the possibility to do something by utilizing the supplementary cementitious materials. What is the basis for the development of low carbon high performance concrete? So there are two, we can say that two. The cement industry has played an important role to treat industrial waste and byproduct, open for 6-9 ton waste byproduct ton per cement. It's quite large amount of the waste and byproduct have been used in the cement production. And in other words, a certain amount of the clinker production should be kept for that. And one idea. And also, the large displacement of the cement with mineral admixtures causes some problems, including low crack resistance and low durability and lower resistance development. In order to overcome these weak points, we need to think something. So that we had a project to overcome that. This is the test cases in which we had to develop the low carbon high performance concrete. We utilized the fly ash and blast furnace slag. And blast furnace slag, the replacement, the cement 20%, 30%, 40%. And then here and there, this is the 10% fly ash replacement and 20% fly ash replacement. And then we found that the CO2 emission in each concrete is like that. And this is the ordinary Portland cement. This is the F20, V20. So it means that almost a 45 reduction in carbon dioxide is achieved. This is 1 point. Not much compared with the 80%, but considering the other performance, like compressive strength development. This is the ordinary Portland cement, and 40% blast furnace slag, and 10% fines, 3% blast furnace slag, and this is the 20% fines and 20% blast furnace slag. So we can see that there is the requirement for the early stage requirement to remove vertical formwork. So in Japan, and that number is 5 Newton per square millimeter. So if you utilize this concrete, that requirement is satisfied. And then finally, 91 days in development is greater than the ordinary Portland cement, as you can see. And we also conducted the shrinkage cracking test utilizing this equipment. This is the Japan Concrete Institute method. This region is the Anchorage region and this region, unbonded region. So the crack occur between this. We cannot evaluate the exact number of the cracking, but we can compare which concrete is better than the others by utilizing this test method. This is the outcome. So if you utilize in 2020, this one, no, this one, the time until the cracking occurs the longest. And if you utilize the ordinary Portland cement, is the shortest. It's a big difference here. You can see that. So, and if we use expansive admixture, so we could not see any cracking. Then we conducted the temperature stress analysis of a constrained wall. So we used the nonlinear temperature stress analysis software, as shown here. And also we calculated homogeneous shrinkage strain using JSC equations. And for the ultimate values of the homogeneous shrinkage, we used test results at the edge of the 91 days. For the expansion strains, we used the test result by the age of the 7 days. Under those conditions, we calculated more like here. So this is the case in which we don't have any supplemental cementitious materials. Inside, the temperature 50 degrees Celsius. But if you look at that, this is the 43.7 degrees Celsius, the drastic decreases. And we calculated cracking index to define these values, Ft divided by Fc. Ft is tensile strength of the concrete, and Fc is the stress of the concrete caused by the heat stress. And then if you look at the water potent cement, the cracking index was 4.7. So it means that 92% possibility of cracking. But if you look at that 2020, so cracking index is 1.4, the possibility is very low. And we calculate considering homogeneous shrinkage. So the condition is more critical. So if you look at the 0.0 ordinary potent cement, 4.7. That's almost we will have the cracking in this case. And if you look at 2020, it's 1.0. Crack occur or not occur, that's critical situation. So you can realize that how the hot shrinkage, homogeneous shrinkage affects the performance of the cracking in the concrete. And this is also considered plus expansion admixture. And if you look at 2020, it's very low possibility of cracking. So we also conducted durability aspect of this concrete, carbonation. So the carbonation rate, FA20B is 20, was the largest. But the carbonation depth is just 31 millimeter with the 100 years. So it means that we can ignore of the carbonation performance. And have a resistance to freeze down. We got the relative dynamic modulus of elasticity in 300 cycles of the 23% approximately. And mass loss was 2.87. So we don't have any problem on the without resistance. How about diffusion coefficient of collodium? And 2020 is better than the ordinary potent cement. So we found that we don't have the particular problem in the durability aspect of this concrete which we developed. So conclusions. This is now fire 20 glass mass 20 concrete, we call it show the excellent performance in flying point. First, 45% reduction in carbon dioxide emission. And second, increase of long-term strength development. Third, we can have the adequate early strength development. And also, we have the high resistance to cracking. And also, we don't see any problem in durability. So this cement, supplementary cementous materials replacement of clinker would be possible at least in Japan, because we have the large steel industry, and also we have the many power plant. So the production of the fly ash and blast furnace slag is quite enough. Even if we introduce 20% blast furnace slag and fly ash, still we have the remaining materials. And we applied this low carbon high performance concrete for the slab wall structure last August. It's shown here. It's a very small structure, but so far we don't have no problem on that. And we are going to apply this concrete to the practical structure in the future. So this project has been conducted in collaboration with Sumitomo Osaka Cement Company Limited and also Hazuma Ando Corporation. Thank you for your attention. The end of the session. So the second speaker is Dr. Higuchi, who comes from the Japan Denka Cement Company. The title of his presentation is the development of a new ecological concrete with carbon dioxide emission below zero.
So thank you, Chairman, and thank you very much for giving us a chance to make a presentation. So my name is Takayuki Higuchi. I'm from Denka, a chemical company in Japan. So we produce cement and special cement additives such as expansive additive and special rapid handling additives. So today I'd like to make a presentation concerning development of a new ecological concrete with carbon dioxide emission below zero. So the reduction of greenhouse gases has become a priority in various industries. So this pie chart is a detail of carbon dioxide emission in Japan. So the electricity industry accounts for approximately 30% carbon dioxide emission. Therefore, the enhancement of thermal efficiency and the expansion of renewable energy sources such as solar, wind, and water has been promoted. In the concrete industry, a lot of carbon dioxide emitted during the production of Portland cement and construction. Therefore, in this situation, a construction company, an electricity company, and cement production company cooperate each other. A new ecological concrete with carbon dioxide emission reduced below zero has been developed. This concrete is named CO2 SICOM. So this is an abbreviation for carbon dioxide storage under infrastructure by concrete materials. The amount of the carbon dioxide emission of ordinary concrete is 200 to 400 kilograms per cubic meter. But this new ecological concrete is below 0 kilogram per cubic meter is a fundamental concept. So this concrete is based on two typical features. The first one is coal ash and gamma C2S, a low carbon dioxide emission substance, are used instead of Portland cement. And the other feature is this concrete is cured with exhaust gas from power station and absorb a lot of carbon dioxide in its concrete. So in the next slide, I'd like to explain the detail of the carbon and gamma C2S. So chemical and physical property of gamma C2S is below. So this substance consists of calcium oxide and silicon dioxide as its principal component. And main mineral composition is gamma type dicalcium silicate. So this is a powdery material, and this substance does not hydrate acetate. So this substance does not hydrate like Portland cement, but it reacts with carbon dioxide under optimum condition. So right figure is the changes the amount of the carbon dioxide during the time of carbonation curing. So the condition is 20% carbon dioxide and 40% degree Celsius, 60% relative humidity. So you can see that the value of the carbon dioxide in gamma C2S increased according to the time of the carbonation curing. So it reached around 40% after 28 days. So gamma C2S react with carbon dioxide and generate calcium carbonate and silicon dioxide gas. So this picture is the backscattered electron image of gamma C2S before carbonation. So these particles are gamma C2S, and black part is particle space. So right figure is the picture of after carbonation. So you can see that the black part decreased and filled by gray substance. And gray substance is consisted of calcium carbonate and silicon dioxide gas. So carbonation increased the volume of gamma C2S to 1.75 times theoretically. So it contributes to decrease the pore and to increase the strength. So this figure is the cumulative pore volume of the paste. Consists of gamma C2S, and cement, and water. The curing condition is 20 degrees Celsius and 60% relative humidity. And the concentration of carbon dioxide is 5%. Curing condition is 60 days and 56 days. So you can see that the cumulative pore volume before carbonation is around 75%. But after carbonation, the value is around 25%, so decreased by carbonation. So right figure is the compressive strength of the same paste specimen. So value before carbonation is around 10 Newton per square meter. On the other hand, after carbonation, the value is over 100 Newton per square meter. The compressive strength increased by carbonation. The production process of gamma C2S is below. So we use the calcium hydroxide and silicon dioxide as its raw material, and they are blended in a theoretical molar ratio and feed them into rotary kiln. Then in the rotary kiln, the calcined over 1400 degrees Celsius and changed into gamma type dicalcium silicate. So this calcium hydroxide is a byproduct and does not emit carbon dioxide in calcination. It's eco-friendly. And clinker changes into powder automatically in cooling process, so it's not necessary to mill the clinker. Therefore, the carbon dioxide emission of gamma C2S is very low. So this figure is the comparison of carbon dioxide emission of ordinary Portland cement and gamma C2S. So the value of ordinary Portland cement is around 800 kg CO2 per ton. On the other hand, the value of gamma C2S is below 200 kg. So it's 1/4 of the ordinary Portland cement. So this 200 CO2 mainly comes from the fuel in calcination. On the other hand, gamma C2S absorbs 400 to 500 kg CO2 per ton in theoretically, so it contributes to the reduction of carbon dioxide. So for silicon and for gamma C2S, which has an environmental performance, one of its advantage, so it's very important how to evaluate the amount of carbon dioxide in concrete. So we tried this problem. So we use the inorganic carbon analyzer as an analytical instrument. So this device enabled the measurement of only inorganic carbon gasified due to decomposition with the acid. So right table is a measurement result, the amount of the carbon dioxide in pure calcite. The theoretical value is 43.97%. On the other hand, the average measurement value of N12305 is 43.95%. So you can see that this device has a good accuracy to detect the carbon dioxide content. And the preparation for analytical sample from the concrete specimen is below. The specimen is cured in water for 24 hours, and volume of the sample is measured by Archimedes method. After that, a sample is dried in 500 degrees Celsius until the weight became constant, and sample weight is measured. And sample is milled under 505 micron. The content of the carbon dioxide is measured by inorganic carbon analyzer. But there is a little bit problem. So in the concrete specimen, the carbon dioxide is absorbed by paste phase mainly. The aggregate does not absorb the carbon dioxide. But the content of the paste and aggregate fluctuate according to the volume of the specimen. So we confirm the effect of the sample size of quantitative value of carbon dioxide content. So in this test, we use this mixed proportion. So we use the limestone powder as the carbon dioxide containing substance. So we replaced them into ordinary bottle cement. And we change the sample volume from 0.1 liter to 1.6 liter, and we measure the carbon dioxide content in concrete specimen. So this is a result of the correlationship between the content of the carbon dioxide in concrete and the sample volume. So you can see that the value averaged around 100 kilograms CO2 per cubic meter, and sample volume increased to 1.6 liter. The fluctuation became small. So the volume about 1.6 liter should be used in order to measure the carbon dioxide content of concrete with good accuracy. So we apply this method to the concrete cured with exhaust gas. So the carbon dioxide emission of raw materials and mixed proportion is below. So we use the glass furnace slag and fly ash and gamma seed waste, a low carbon dioxide emission substance instead of powder cement, and we manufacture the concrete specimen. And right picture is the carbonation curing chamber at Misumi Power Station on Chuo Electric Power in Japan. This yellow part is the carbonation curing chamber. So the exhaust gas was launched into the curing vessel, this carbonation curing chamber, after adjusting the temperature 50 degrees Celsius and the relative humidity 50% along this red arrow. And the carbon dioxide concentration were between 15 and 20%. This picture is inside of the carbonation curing chamber, and the paving blocks and border blocks are cured in this chamber, like this. So this is the result of the carbon dioxide emission of standard concrete and silicon concrete. So this blue bar is the amount of the carbon dioxide emission from the material. So you can see that the value of silicon is 90.6 kilograms per cubic meter, reduced by replacing the gamma C2S and the fly ash and blast furnace slag. On the other hand, the green bar is the amount of the carbon dioxide fixation by cured with exhaust gas. So it was getting larger than standard concrete. So it reached 104.5 kilogram CO2 per cubic meter. So it was surpassed the amount of the carbon dioxide emitted from material. So the total amount of carbon dioxide emitted can be reduced to below 0 kilogram in CO2 cycle. Finally, I'd like to explain the properties of concrete. For example, strength, drying shrinkage, and effervescence. So this figure is a result of the complexing strength, so according to the carbonation flowing. So you can see that the complexing strength increased the carbonation according to the carbonation flowing. So it reached around 30 Newton per square meter at 14 days. The carbonation proceeds into the middle of the part, middle of the concrete specimen at 14 days. After that, the compressing strength did not change to 28 days. So this figure is the result of drying shrinkage of the concrete. The measurement condition is 20 degrees Celsius and 60% relative humidity. And we cured the specimen in 14 days. And the drying shrinkage of silicon is very low, lower than ordinary concrete. And it kept the constant value. And we assume that the carbonation and hydration had already finished before the test. So the CO2 silicon concrete kept a low drying shrinkage. And this picture is an example of the effervescence. So you can see that effervescence on the normal block, like this white substance. On the other hand, effervescence is controlled in CO2 silicon. So alkaline substance is carbonated in the middle of the concrete, so it does not appear on the surface. And the pH value of CO2 silicon is close to neutral by carbonation. So this condition suits for growth of the plant. So CO2 silicon harmonizes well to the environment. So we already applied this CO2 silicon to mega solar power station for sustainability facility, like paving block and border block. And 2 years have already passed after installation. And we have been monitoring the situation of concrete. So modern Portland cement is alkaline, so if it neutralizes from the surface with steel rod, so it generates corrosion. Therefore, it's not easy to apply CO2 silicon to reinforced concrete. On the other hand, the volcanic ash and limes and carbon dioxide are used for ancient concrete. Since the steel rod is not employed, the strength is persisting for thousands of years. So we hope that the CO2 silicon contribute to the sustainability of concrete industry, like ancient concrete. The conclusion is below. The gamma C2S does not hydrate, but it reacts with carbon dioxide. The content of carbon dioxide fixation reached about 40% after 28 days. And a volume of about 1.6 liters should be used in order to measure the carbon dioxide content of concrete with good accuracy. So by choosing appropriate powder for position and by applying the proper carbonation flowing, the amount of carbon dioxide emitted reduced below zero. So finally, the CO2 silicon has many features such as dimension stabilization, environmental harmonization, and resistance to effervescence. So thank you for your attention.
Thank you, Mr. Higuchi. It's very interesting presentation. He introduced the name of this good, suikon, which Japanese means absorbing. Just interesting naming. But we have the a few minutes if you have the question or comment, please. Yes.
When was the work done?
What then?
When was the project work done?
In this context, it continue. Yes.
When did it start?
Yes.
This project started 7 years ago.
7 years ago.
We have a question from the webinar audience. The question is, can you clarify the method of calculation of CO2 emission in the sample concrete?
So I repeat, we use the inorganic carbon analyzer to detect the carbon dioxide content. So this method, this device enables the measurement of only inorganic carbon gasified due to decomposition with the acid. And the sample is cured. At first, the sample volume we measured, and after drying, the sample is milled under 505 micron, and the content of the carbon dioxide by the inorganic carbon analyzer, and calculate the content of carbon dioxide using the volume of the specimen. So change to the carbon dioxide content per cubic.
I think that the PowerPoint is uploading on the ACI website, so he or she can look at that, the details. Yes?
Yes, any idea of the added cost to vinyl concrete based on the process? If you're adding this material, what's the increase in cost for the concrete? Do you have any idea of that?
So I cannot answer the precise cost. So your question is very good. So there's a big problem. So the cost is quite high compared to the original contract. So we are now challenging.
It seems to me it doesn't cost much because just put the specimen in the chamber. There is no extra things. Yes, please.
Have you done additional work to look at the different phases that you're getting regarding the calcium carbonate that's being produced when you cool down your cement? Have you done additional work to look at what type of phases you're getting produced? Are you assuming that it's calcite?
Yes, generally calcite.
Okay. And you've done analysis to make sure?
Yes, we confirm.
The last one, if you have. No question? So, thank you so much. So next presentation is will be done by Mr. Laurent Barcel from Canada, Laforge. The title of the presentation is A Path Towards More Sustainable Cement Manufacturing.
Thank you very much, Mr. Chairman. So this presentation is entitled A Path Forward Towards More Sustainable Cement Manufacturing. And I have a fairly lengthy introduction, so I would need your help. There is a little quiz. I would like to know if you have an idea what this number is. And last time I checked, it was not on the statement of my bank account. So, any idea? So this was an estimation of the world population about a week ago on October 11 at 9:54 a.m. And I did check about 5 minutes later, and this number had increased by 850. So this is the big challenge we have. Another quiz. What is that? Projection of what? No. No, it's not a projection. Actually, these are tons. And it's a conservative estimation of the amount of concrete produced every year on the planet. It's a conservative estimation. So it's about 2 tons per inhabitant. It's massive. And there are good reasons for this. The first one is cost. Concrete is quite very cost effective. So on this graph here, it's taken from a material science textbook. You have on this axis the price of the materials and the annual production here. And you see concrete here is on the low cost, high amount of annual production. And this is power of 10. So for every ton of this, you have about 10 kg of something here, and you have about 100 grams of something here. So the scale is massive, the amount of concrete produced on the planet. And also, all these products here have limited reserves, and with concrete, with majority being limestone, we have a lot of reserves. So cost, local availability in large quantities is also a reason, ease of use, sometimes, unfortunately, relative robustness to misuse, versatility, durability when it's well done. So very good reasons for this, and it's not going to end. And the projections from the international energy agencies are that between now and 2050, the cement production is expecting to grow by 40 to 50%. You know that today, over half of the world production of cement is in China, and it's expected that this number is going to peak by 2015 to 2020, and the production in China is expected to decrease when they have built their infrastructure. And but other countries are going to take off. So cement consumption or cement production is expected to grow very significantly. And this popularity comes at a cost. It turns a material that has intrinsic low carbon emissions into a significant contributor to man-made CO2 emissions. And you probably all know that globally, cement manufacturing is responsible for 5% of GHG emissions. And this is really the reasons why. Because if you look at on a per ton basis, and I put on this graph results I extracted from a study from the University of Bath in the UK. We have on this axis the CO2 footprint, and on this axis here you have the energy footprint. And again, these are power of tens on each axis. And you can see that concrete here is very, very well positioned, very low CO2, very low energy. And again, I understand that tons to tons comparisons are not fair, and that what we should do is a full LCA on a specific project. But this puts number into perspective, and I think that we would not speak about CO2 in the cement and concrete industry if we would produce as much cement as we produce steel, for instance, every year. So really, we are victim of the very large volumes. So these CO2 emissions in cement manufacturing, where are they coming from? So the first one is the CO2 from the calcination of limestone. So Ca, CO3 becoming CaO plus CO2. And it's about 535 kilograms of CO2 per ton of clinker. And this number is fairly constant from plant to plant. The second one is the CO2 from fuel combustion. And it's about 330 kilograms of CO2 per ton of clinker. So you see it's a 60-40 split between the decarbonation and the fuels. But this number, you can see larger variation from plant to plant depending on the process that the plants are using. You add these two, and you have the direct CO2 emissions for clinker. So it's about 865 kilograms of CO2 per ton of clinker. And this excludes the CO2 from electricity, which is the indirect CO2 emission. But we know that in the case of clinker and cement manufacturing, it's rather small. It's about 10% of the total CO2 emission. We also know that cement is not 100% clinker. So in fact, in 2006, CSI made a survey, and they find out that the worldwide average was 78% clinker in cement. So when you multiply these two, you have the direct CO2 emissions for cement manufacturing, which is about 680 kilograms of CO2 per ton of cement. And you see it's quite far from the 1 ton of CO2 per ton of cement that we hear very often. I understand that 1 ton is easy to remember, but I mean, it's really not 1 ton. So with that, the content of, after this lengthy introduction, the content of my presentation today. So first, we are going to look at the bigger picture and what the industry has been doing to improve the CO2 footprint. In the second part, we are going to look into to what extent we can reduce the CO2 footprint further through clinker formulation. And finally, we are going to evaluate an innovative solution that we are proposing. So let's start with the bigger picture. And we start with the International Energy Agency with this blue map scenario. So these blue map scenarios, the International Energy Agency, IEA, they were mandated by G20 to work on long-term scenarios for carbon reduction. And when we say long-term, we mean 2050 here. And they made an update in 2012, and they provide 3 scenarios. A business as usual scenario where they say the temperature is going to increase by plus 6 degrees Celsius. It's about 11 Fahrenheit. And they also provided plus 4 and plus 2 degrees Celsius scenario. One important thing for us is that they are promoting a sectorial approach, meaning they recognize that it will be counterproductive to ask for the same amount of reduction in every sector, and in fact it would be it would cost more to society. So they really this sectorial approach is really favorable to us. And also they led the development of technology roadmaps in key areas, and there is one for cement technology that is available, and I would encourage everyone to read it. It's not a very large document. So if we look at the global picture, in 2027, worldwide, we have emitted about 30 billion tons of CO2. And if we do nothing, by 2050, it's expected that the emissions will double. And the blue map scenario that to restrain the temperature increase by 5 degrees Fahrenheit says that we should cut by half compared to 2007, or by 4 compared to the baseline. So because of this sectorial approach, the situation is different for cement. So what it is for cement? So in 2007, the cement industry was responsible for 2 billion tons of CO2 emission. The business as usual would mean 2.34 billion tons by 2050, and what is expected for the industry is to go down to 155. So it's a 23% reduction compared to 2007 over 43 years. So you could say that it's not a huge effort, but you need to factor in that during the same time, the cement production is going to increase by 40 to 50%. So when you factor in this thing, you see that per ton of cement, the CO2 emission is expected to go from 680 kilo of CO2 per ton of cement to somewhere between 300 to 400 kilograms of CO2 per ton of cement. So the cement industry has been using 3 main levers to reduce the CO2 emissions. The first one, energy efficiency. Second one, alternative fuels and use of biomass. And the third one, clinker substitution. So the 2 first, they are really playing here on this number, which is the CO2 from fuel combustion. And the third one, the clinker substitution, is a very powerful lever because it's this multiplicator lever here that reduces the overall CO2. And we are going to take a look at each of these one by one. So energy efficiency first. So here I have reported the energy efficiency for the different type of processes in gigajoules per ton of cement. So you see that the old wet kilns, they were really in the range of 6 gigajoules per ton of cement. And the more modern kilns, so you have the long dry, the preheater, precalciner, the more modern, what the industry considers today as the best available technology is the 5 stages preheater with precalciner, is at 3 gigajoules per ton of cement. So it's about 50% more efficient than the old wet kiln. And when you look at the what is the theoretical energy consumption you need just for the chemical reaction that happens inside the kiln, you see that you need 1.75, so that means that your efficiency with this best available technology is 58%, which is quite good. In fact, it's better than the engine we have in the car. On this map, we have the evolution of the average clean consumption in the US, and you see that the improvement over the decades. So I have reported here the best available technology and the theoretical minimum. And so I just have 2008 here, but with the crisis and the older plants that have been shut down in the 2-3 last years, I would expect that this number now is even much better than it used to be. So energy efficiency. The second level is use of alternative fuels and biomass. And on this chart here, I'm plotting the examples of average use of alternative fuels in different countries for cement manufacturing. And you see that North America, here we are in the middle of the pack, and we could really do a little bit better. You have some countries in Western Europe that use a much larger quantity of alternative fuels and biomass in their field. Really somewhere, it's an area where we can improve. The third one is about clinker substitution. So you know all these cementary cementitious materials that the industry is using. So we have slag, type C, type F ash, metakaolin, very important, limestone, and a very important one is the type 1L cement that was just adopted in C595. So clinker substitution is very important. Again, I have a similar type of graph. Average clinker substitution in different regions of the world, and you can see that here, North America is a little bit lagging behind. So it's quite old data, but I don't think the numbers have changed dramatically. And it's also an area where you can improve the situation in North America. Countries leading the game are China, India, countries in Latin America, and Europe. So when you put all this together, what the experts from IEA and the Cement Sustainability Initiative are saying is that when you look at where we are, 2 billion tons, we need to reach 155. If we just use these 3 levers, we are going to move from here to here. So it will be we are going to be far from reaching the target. And what they say, okay, the rest is going to be carbon capture and sequestration. So first, carbon capture and sequestration is not today a technology that is mature, and it's going to be very expensive. So it's going to increase significantly the cost of cement if you go that way. So we said maybe there is something else we can do. And it leads to my the second part of my talk on to what extent through changes in the Portland cement clinker formulation we can further decrease the CO2 footprint of cement. So we have to decrease these 2 numbers here, the CO2 from the limestone calcination and the CO2 from the fuels combustion. What I try to do first is to explain what happens in the kiln CO2-wise and energy-wise when we want to produce C3S. That is the main component of modern cements. So the first reaction that happens in the kiln is the decarbonation of limestone. CaCO3 becomes CaO plus CO2, and here we have the release of the CO2 from the limestone. And in order to drive this reaction, we need a massive amount of energy, which translates into fuels that we need to burn in order for that reaction to happen. After that, we have the formation of C2S from the lime that is being produced here and the silica that we put in the raw mix to form C2S. And this reaction indeed releases a little bit of heat. And finally, C2S combines with additional CaO to form C3S. And we have the overall C3S balance here with 1.85 gigajoules per ton of C3S. So you can see here the double penalty with high limestone cements. We have a high amount of CO2 released by the decarbonation. And we have to go through this massive energy consumption for the decarbonation that translates into fuel. So double penalty for high lime system. So here I have calculated the CO2 footprint for the different phases of Portland cement. So this is in kilogram of CO2 per ton of phase. You have C3R, C2R, C3A, and C4R. The blue portion is the CO2 coming from the decarbonation, and the red portion is the CO2 coming from the fuels. And this is calculated assuming a very modern plant, 5 stages per liter with precalcite. As what you can see is that really the C3Rs and the C3A are the two phases that have the higher CO2 footprint. So we can wonder, okay, why not? Why won't we go through C2S type of clinker? And why not we would eliminate C3Rs and make a clinker which is only C2Rs and C3A and C4A, because we need a little bit of liquid phase in the kiln in order for the clinkering reaction, but why not going there? So if we would go there, the CO2 footprint of the cement would be reduced by 12%. And you can see, so we would go from 816 to 719, and you can see that the bulk of the reduction would come from the fuels, and indeed we would have a minute reduction of the CO2 from the raw materials. So is it the way to go? I mean, we are not sure, because CO2 footprint is rather limited. It's 12%. We see that we have a very significant reduction amount in front of us. And the second aspect is that if we go that way, chances are that we are going to impact negatively the early reactivity of cement, and in consequence, we won't be able to use a lot of SCMs in cement. So instead, we are proposing an out-of-the-box solution. So what are the characteristics of the solution we are looking? So we are looking for clinker that leverage all the current clinker advantages, so something that is available largely locally, which is cheap, so nothing fancy, with a high level of early reactivity, at least the one of OPC, to work well with SCM, and that would be durable, including steel protection, so which discards all the solution with CO2 curing and so on. And in addition, we would like a much lower CIO content in order to drive down the CO2 emission, and we would like this to be able to be manufactured in existing plants, because the plant is fairly expensive. So what we are proposing is BCSIF clinkers, and we have trade named them ESA. So B stands for B-light, and here it's really activated B-light that we are using. We are using boron to dope B-light, and it's a different polymorph of B-light that we are doing, which is more reactive than the B-light we find typically in OPC. So we still produce CSH for later age strengths. CSA is the calcio-sulfur-eliminate phase, and we produce stable ettringite that gives the early age reactivity. And F stands for ferrite, and ferrite is also quite important because it reacts, and there is a coupled reaction with B-light to form spontanite. And the results of all these that we can develop equivalent strengths for a lower carbon footprint. How much lower? So we've seen that ordinary cement is at 816. With the theoretical C2S, we are down by 12%. With this approach, we are down by 30%. And what's very important here, you can see that we significantly reduce the CO2 coming from the raw materials, as well as reducing the CO2 coming from the fuels. Where it is in this CIO, SiO2, L2O3 diagram, so it's about here. So you see it's not very far from ordinary Portland cement. Of course, there is a fourth dimension because there is the sulfate. So the B-light is between 40 to 75%, so it's still the main phase. The calcium sulfur eliminate is 15 to 35%, and we still have 5 to 25% here. So how can we achieve such a performance? So you see that C3S and C3A, they were the phases with the higher CO2 footprint. We don't have them in this cement. So instead, the main phase is C2S. We have a little bit of C4AF, and we have a significant amount of this calcium sulfurylate phase. And you see that the CO2 footprint of this phase is very, very interesting, both on the raw material CO2 and on the fuel. So the key benefits of this, so first, as we've seen, 30% reduction of the CO2 footprint. We have an additional saving on CO2 from electricity because these clinkers are easier to grind. We have a high level of reactivity that allows to maintain a high level of SCM substitution. So we are not making trade-off on that aspect. We have a later strength development that is similar to OPC, and it can be manufactured in existing cement plants. We don't need heavy capital expenditures, and we can even potentially increase production rates because we are decreasing the burning temperature. And we have already demonstrated that at industrial scale in real kilns, both on older generation and on newer generation type of kilns. And here we have an example on concrete made for precast application with this cement. So we had a slump larger than 100 centimeter, slump retention, 45 minutes to 1 hour for this precast application. The strength development, very interesting. So 2900 psi at 6 hours with no heat, 3900 psi at 1 day, and 7000 psi at 28 days. Of course, we have a few challenges. The cost of raw materials can be a little bit higher. This is because we need more alumina in the raw meat. So some level of taxation of CO2 needs to happen to make this commercially viable at large scale. But the overcost, nevertheless, is very small, and it's very small compared to the alternatives such as CCS and so on. The other aspect is that in cement and concrete science, we have 100 years plus of R&D, and we are still scratching our head. So you can imagine that here with I think 7 years of development, we just have scratched the surface of it. So things are going to evolve, but and finally specs, customer acceptance, and so on. These are going to be challenges that we are going to face. So with that, I thank you for your attention.
Thank you, Mr. Nubarcelo. And our last speaker of this first session is the Professor Harald Müller, who came from the Karlsruhe Institute of Technology, Germany. The title of his presentation today is Sustainable Concrete Structure Through Service Life Design and Eco-Efficient Concrete.
Thank you, Coach. Ladies and gentlemen, I'm going to talk about sustainable concrete structures, and I will show you two different approaches how this sustainability can be achieved. First, thinking of sustainability, we have to define what we understand of it, and I make a very simple formula, pushing aside social aspects and political aspects. If we look in this case to sustainability, you see it is a product of service life, of performance of concrete, divided by the environmental impact. And if we now look to service life, it has to be maximized, of course, to make a concrete structure sustainable. If we look to the performance, it has also to be maximized to achieve a high sustainability. And third, if you look to the environmental impact, we have to minimize as it is lower than the sustainability is higher. Now I will deal with these three different approaches in a little bit more detail. First, the service life approach. Increased service life can be achieved by an adequate service life design method. Second, by an improved monitoring and structural inspection, or by adequate rehabilitation work. And another aspect is to keep the structure attractive to the user. So, if we look to the service life design, everybody of you knows this particular damages which occurs in practice. It can be sketched in a way as I did it here. We have actions on our structure, and we have the resistance from the concrete over the age of the structure. And if the actions are lower than the resistance, we have no damage. Both are scattering, and if the scatter range is overlapped, damages occur. If we look to the damages, it is the second diagram, level of deterioration on the y-axis and the age of the structure. We have first only an initiation period, and then when the overlap came, first damages, they increase until finally a collapse occurs. This is a situation in practice we have, and now we deal with this situation in our design. We apply in all countries so far a descriptive concept. We have a very simple approach. Resistance must be higher than actions. And if you plot this in the diagram, you see it's completely different than the one I have shown before. We look to an average age of 50 years. We assume to be there a safety margin in between. And the method we apply is the actions are defined by ambient conditions, and the resistance by some parameters of the concrete. Maximum water cement ratio, minimum strength, minimum cement content, and concrete cover. And what is if our structure is only intended for 20 years or 10 years? And what about 100 years? 100 years is by far too low. For 20 years, 10 years is too much. We waste concrete, we waste cement, because we have a wrong, a very crude design approach so far. Much better is a performance concept. You have the same formula here, but now you have the phase of mobility, and you calculate with time. And you have an additional parameter, which is the target or the phase of mobility. This means it is a limit state. You define a limit state. And now you can have functions of the resistance and the actions, and you see here I can scale now the axis. Here is nothing scaled now, and now I can do an exact calculation of resistance and the actions, and then I can calculate how much cover I need and so in all the parameters. This is realized in FRD Model Code 2010. How this method works. If we look to the very simple example, carbonation-induced corrosion, then that is the basic formula for the design approach. Your resistance and the concrete cover, you have the carbonation process. And important is normally we do not talk about failure probability, we talk on reliability. It sounds much more better. It is from a mathematical point of view the same, but it's better to speak of reliability than of failure probability. And if we look to the result, then we get the reliability index better calculated from this formula over the age of the structure. This is a design situation where the owner, for example, defined the service life of his structure, and this the beta hardship may be defined upon the damage which I am ready to accept, or the risk, or the owner's interest, or something else. You are free to do it in your calculation. Let me give you an example, a very simple example. If you have, for example, a tunnel. You have a tunnel on top, the walls, and the floor, and the boundary conditions are you will have a service life of 100 years. You accept 5% of damages, which means a reliability index of 1.7, and your limit state is a depassivation of the reinforcement. Then it was carried out, and if we now look, for example, just to the concrete cover, this was the design values we have a mean cover of 55 millimeter and a standard deviation, which is unavoidable, of 8 millimeter. Then we arrive at the age of life age of 100 years. For example, if there is a bad encroachment and we have a mean average of the concrete cover of 55, but a standard deviation of 60 millimeter, you see that the age at the achievement of the limit state reduces to 60 years. This is a tremendous difference. 40 years earlier, there are much more damages. Or on the other hand, if there is a misunderstanding, for example, you have just a mean value of 45 instead of 55 millimeter concrete cover, but you have the encroachment, those standard deviation, you end up due to this difference at 62 years. This indicates you very clearly how sensitive you can do calculations with this new type of method. You don't waste material if you apply these methods. This is just a simple example to make clear what is the power. But what is most important is I just show you one element and one process. Reality is much more complex. Reality means we have a structure. A structure is a system which must be analyzed. We must do a failure probability analysis, and we must also do a risk assessment. This sounds a little bit huge for concrete people, but if you look to the aircraft industry, this is a system which is well developed. And if we look, for example, then to a structure, for example, a superstructure of a bridge, we have to make an element breakdown, which can be rather simple. And we have to assign to the individual components, the carriage slab, the caps, the webs, and the tension and the compression cord, the major exposure conditions, and we have to define the critical ones. For example, the critical ones for the carriageway slab is the chloride-induced corrosion. And though you go through and you define an easy procedure, the major exposure condition and the critical events. And then you have to bring those things together in a force tree, type of force tree in the superstructure. Very easy done here if you have chloride corrosion, induced corrosion or carbonation, or for example also alkali reaction or corrosion of tendons. All those may lead to a complete failure. But they interact. And there is a further parameter, just a simple one. We know that chlorides and carbonation have a particular interaction. Carbonation may release chloride which have been bonded before. So doing this calculation, we have to take those things into consideration, and this may actually be done. If we have no interaction, but different action on different parts of our materials, this result is obtained by this design, reliability, again, of the age of the structure. If you have, you see here the boundary condition, intended service life, 100 years, different limit states due to different actions, the preservation of the reinforcement, weathering of the concrete cover, and corrosion of tendons. You have here the decreasing reliability for carbonation and chloride. You end up at 95 years. Plant has been 100 years. If you have, in addition, an alkali silica reaction by a certain probability, you see you end up already at 85 years. And you have also, if you have also corroding tendons, then the curve is much lower. If you have your limit state at 1.6 as a reliability index. You see how this system can be used to give an answer if you have a much more complexer structure. And these interactions, I mentioned it for chlorides and carbonation, are also very sensitive and have to be looked into detail. If we look, for example, for a time of assessment of 50 years, and we include for the diffusion coefficient, a combination factor at carbo, and we said it is 0, it is 1.0, then we have no interaction, we have our design age 50 years without any interaction. Limits the safety factor about 1.6. Now, if we, for example, have a lower value of new carbo, we have an increased pore volume, which means to a lower failability and a higher reliability index. It is vice versa if this factor increases. This means we have to determine this factor very exactly, and the differences are rather large. So I could more go into detail, but I have some other subjects, so I'll switch to the next one. I look to the second approach, and the second approach means to minimize environmental impact. We have already heard in the previous presentations that we have to use other materials, composite cements, and so on. We have to develop concrete with a reduced binder or cement clinker concrete, and we have to apply environmental friendly production and building techniques. I will focus on the environmental impact in a little bit different way than has been done before. If you look at the standards which are available, we have categorization in 6 classes. We have to look on 6 different categories. This is primary energy, this global warmer potential, CO2, but ozone depletion, artification potential, nuclearization potential, and photochemical ozone depletion. If we look to our concrete making materials, and in these categories, and when you see here the raw materials, cement, different cement, fly ash, slag, limestone, and so on, and here the 6 categories I mentioned right before, and you have a lot of figures. You must not read them in detail. They are delivered to you because there is an environmental product declaration, which since the year 2013 in Germany must be delivered by the producer of the raw material. And there you can read in detail the ecological impact of all those parts. And if we apply this table for an ordinary concrete and add up, you have here again these parameters. You have ordinary concrete, and here the fraction, and you see blue is cement, red additives, and yellow are the aggregates. You can see that so the aggregate amount is the largest one, the impact is low, but most of those lines, the blue is dominating. This means if we would like to change things, we have to look to cement. Only if we look to the additives, in some cases where we use a lot of additives, then here also some effects are adverse concerning the production of concrete. But the cement is a decisive part. Now we can consider what to do. The thing is, use as low cement as possible. We have to look what is the binder intensity. This means the amount of cement per cubic meter of concrete divided by the compressive strength. If we do this for traditional concrete compositions, we find points like plotted here, and you see the higher the compressive stress we realize, the lower is the cement content used to gain this high strength. This means there is much room for improvement for low strength concrete, and much lower room or no more room for high strength concrete. It's better, and also Professor Sakai mentioned it, to produce high strength concrete. It's very clear from this relation. I focus now on much high strength concrete, ultra high strength concrete, and also what we can do with the low strength concrete. So if we apply this, or if we produce an eco-efficient concrete, they may be composed as we showed for concrete number 1, 3, and 6. You have here the reference, for the average content of cement of the concrete, 320 kilogram per cubic meter. The aggregates, the water cement ratio 0.5. You end up with a compressive strength of 45. Now you can replace more and more the Portland cement. You see, you reduce it to 1/3 and even to 1/6 here. You have to fill up with fly ash, with slag sand, bottom ash, and ground it. But you may end up finally with a similar compressive strength at the age of 28 days. This is actually no problem, even if you use only 50 kilogram of Portland cement. And if you now do the equivalence, and I do it in a radar chart or in a spider mesh where you have on the axis the criterion I have explained before, and I normalize it to the reference concrete. This means reference concrete would be always 1 on this individual axis. You can see that the concrete 1 is much better than the reference concrete, and the concrete 6, of course, it's clear, seems to be the best in this radar chart of sustainability. But, as already has been mentioned, there is a problem insofar to gain the strength is no problem, but to gain durability, that's the problem. The frost resistance of this concrete is very bad. After 10 cycles, he crosses the limits, and insofar it is not suitable in cases where we have a frost attack on the concrete. My last approach is to look to the performance. The performance may be increased by increased strength and durability, by materials to be applied with additional functionality, and by an increasement of the resilience. Everybody knows if you reduce the water binder ratio, we arrive to high strength concrete, and for very low water binder ratios, we arrive at ultra high strength concrete, which can have a very, very high strength. At the same time, when reducing the water binder ratio, we have an increase of the resistance against chemical attack and other attack, and the key goal behind is the minimization of the porosity, and the basic requirements means a low water binder ratio, but at the same time we need a sufficient workability, and then we must use superplasticizer as mixtures, and we must develop and optimize granular packing. There is much potential in this, but I don't go into details. I look to the other part. I look now to what may be done if we go to very high strength concrete, ultra high strength concrete. Sorry, one moment. Okay, if we look to this concrete, you see for high performance concrete, you need much more cement, which at first sight appears to be rather negative. 600 kilograms of cement per cubic meter, then microsilica and all that, and also steel fibers to make a ultra high performance concrete. It looks not to be very sustainable. However, the technical performance of this material is excellent. You arrive at compressive strength very easily up to 200 megapascal. Everybody can do it in his lab. And if you apply a curing, a special curing, a little bit of temperature or additional pressure, you're way up and between 800, nearly 1,000 megapascal. Here the strain behavior is plotted on the right-hand side. Compressive stress over the concrete strain. You see nearly a linear behavior. This is a normal strength concrete strain behavior. This is the ultra high performance concrete. We produce it normally with fiber and material. If we now look to its sustainability, and we make the classical comparison, we have here the ordinary concrete, again the same radar chart which I already explained. We have here the ordinary concrete and here the ultra high performance concrete. Much less. But nobody really should compare it on the basis of 1 cubic meter. You should compare different materials in view of their performance. And if we do such a comparison, we can first do the reference basis for compressive strength, And if you then look to it, you can see that the ultra-high performance concrete, though you need a lot of cement, other additions, end up in a much better ecological footprint than the ordinary concrete. And in particular, if you look to durability, and you take the permeability of the concrete or porosity as a measure, then this is your ultra-high performance concrete, and that's your ordinary concrete. This clearly indicates that increase in strength, a very high increase in strength, leads to more sustainable concrete and materials. Let me sum up. The sustainability of concrete and concrete structures will be increased by increased durability and by application of service life design, by reduced environmental impact of the raw material, or by an increased performance of concrete and the whole structure, or combinations of this. I focus 3 major points. It is service life design. It allows, you end up with much better predictions if you use, in view of material degradation with this approach, and you end up with the optimum service life design. Then if you use an eco-efficient concrete, you must apply new types of concrete with strongly reduced cement concrete while keeping high performance. This can be done, not completely. There are some open questions in this, also some open questions here. And high performance concrete, I showed that the development of those concretes with strongly increased strength and durability ensure a maximum of performance. The problems we have are manifold. First, we need adequate material laws, in particular to predict the degradation behavior. I showed you some of these models now we have to further develop. It is not enough. There are a lot of open questions in it, but it is already based in a guideline in the Model Code 2010. And what is also needed is that we understand the mechanism to decouple concrete strength and concrete durability. Mostly we increase strength and we reduce at the same time the water-cement ratio, and then we increase durability. So the advantage to uncouple both, to have a concrete with a low strength and a high durability, which is difficult to produce for the time being. Thank you very much.
Thank you, Harold. Professor Mueller is right now Vice President of FIB and the future President. We can have the one quick question. Yes.
Professor Mueller, thank you. It's a very advanced and very interesting presentation. I have 3 quick questions that you can just give quick answer. First one, your definition of that equation, service lifetime performance divided by environmental impact. It's very difficult to define environmental impact as a single number. So you will have a difficulty to define that quantitatively, I think. Second one,
My answer is very simple. The answer is this simple formula should just show you the general tendencies. I cannot calculate the number of it. We have no measure for such a number. But it should just indicate where are the points where we should change, introduce changes to achieve to a higher sustainability.
Yeah, formula-wise, I completely agree with you. Yeah. The second one, biointensity. I think it's a very interesting concept. We also doing similar research in Korea. So I just wonder if you want to apply this kind of concept in your standard or specification in the future.
Sorry, I didn't get the first.
Binder intensity. You mentioned about binder intensity.
Okay, binder intensity. Yes. Right. In our country, we have first the guidelines, you have no chance to produce concrete for practice with very low cement contents. But we have a certain approval system. And the approval authority, with some experts, which are able to allow people under certain conditions to produce concrete which differ from the guidelines. And within this institution now there are some applications which are being dealt now for concrete with having only a cement content of around about 100 kilograms per ton cement, not more. It's a special system to be developed to open the market for these new types of concrete.
Yeah. Again, I agree that such concept is very much needed. I wonder if I have time for the third question or not. If it's not, then I will talk during the break. Or as it's about the eco-balance. There is a very interesting index we can utilize. But you mentioned about 6 or 7 impact categories. Is it your own research purpose defined categories, or is more nationally or more recognized category in Europe? That's my last question.
These are the international accepted categories. Now, this is not done in council at my institute, not at all. There are ISO and others who have developed it. When we just use it, and all those figures we just use it to show how the different concretes behave in this system.
Yeah, that's correct. But eco-balance, you specifically mentioned about 6 or 7 categories. So it's not ISO. I just wondered where it came from.
I think that we can continue this discussion in the panel discussion. Okay? So thank you very much. And I'd like to close the first session. And the second session will start 3:10. Okay, so please come back 3:10. Okay, I think that it's time to restart the session. Okay. The first speaker of the second session is Dr. Noguchi, who came from the University of Tokyo. He's going to talk about the ISO standardization on environmental issues for the concrete sector.
Good afternoon, ladies and gentlemen. My name is Takafumi Noguchi from the University of Tokyo. So today I would like to speak about the ISO standardization on environmental issues for concrete sector. This is the third time to introduce the ISO activities on the standardization of the environmental issues in concrete sector. First one is in Pittsburgh, 2010, and the next is Cincinnati. It was 2011. This is the third time. But we have proceeded the activities to establish this ISO standard on environmental issues. First of all, I'd like to introduce the ISO activities related to the environmental issues of the concrete sector and the construction sector. You can see here the DC 207. They are establishing the environmental standard for all of the products and activities. And the TC59, this technical committee is for the building and civil engineering works. They are servicing the sustainability in building and civil engineering works, considering the environmental issues. And also TC205. This is specific for the building environmental design, especially the indoor environment. and energy efficiency of the building. And then TC71. This is our technical committee, which is related to the concrete, reinforced concrete, and pressureless concrete. And we have subcommittee 8, which deal with environmental management for concrete and concrete structures. This subcommittee is now established under some ISO standards. So this is a hierarchy of the ISO standardization for any product. We have to refer the ISO 14000 series. Based on these standards, some standards are established for the construction of building and civil engineering works. To make a standard in concrete, we have to base and refer to these standards, 14000 series, and also the ISO standards established in TC 59. We will make a plan to establish the 8 parts of ISO 13315, environmental management for concrete and concrete structures. This TC71 subcommittee 8 was established in 2007, and we have already 5 meetings every year. And the next meeting will be held in Sydney, Australia. And this subcommittee 8 is chaired by Professor Koji Sakai, is here, and the secretariat is Japan, and I am in charge of secretary. Now we have 13 participating countries, active members, and observing country 10 members. So United States is a participating country. They are very active to establish ISO standard on environmental issues in concrete. And this is 8 parts. The part 1 has already been established in 2012. Now, the part 2 is under establishment. It is draft international stage. Probably the next year, it will be IS. And then the next year, part 4, environmental design of concrete structures, and part 8, rather than declaration. We have working group to investigate the new standardization. And another working group will be established after the next. Okay, so I will introduce very simply the it has already established part 1. That this shows the table of contents. This part 1 specifies the general framework of all parts. can see here the phases in the life cycle and the environmental impact category, and how to analyze the environmental impact in the life cycle, and also how to design the environmental issues in the concrete structures, and how to reduce the environmental impact in the production execution phase, use phase, and end phase. So this is the life cycle we are dealing with. First, the design phase, then production execution phase, use phase, and end phase. In each phase, we have to verify the performance of environment will meet the requirement. And then, after the phase, we have to inspect the environmental impact generated in each phase to meet the requirement or not. And then it will meet the requirement, the label and declaration will be given to the products or the technology. In part 1, we have categorized the environmental impact in the impact, the global climate change, natural resource use, land use, eutrophication, acidification, air pollution, and so on. So in these categories, we have to evaluate, estimate, evaluate, and verify the impact to meet the requirement. This table is shown in the next of part 1. So you can see here in the design phase, in production execution phase, we have to care about the carbon dioxide emission in the production of the cement, and also in the production of aggregate. And in the production phase, we have to care about fossil fuel or metallic mineral in the cement production, like this. And also in the design phase, we can consider the environmental benefit and load mitigation by service life extension. It should be in the design phase. And also, the multifunctional design can contribute to the reduction of the environmental impact. In the material supply phase, for the production of the aggregate, the use of industrial byproduct can be considered as a beneficial impact. At the end phase, we may consider the CO2 uptake after the emission structures and recycling phase and the disposal phase. Like this table shows the environmental impact which should be considered in the which phase, and also which impact should be considered in the each phase. And part 1, how to reduce the environmental impact in each phase are described like this. the execution of concrete structure shall be carried out to reduce energy consumption and waste generation during the procurement, scaffolding, forming, reinforcing, completing, curing, erection of precast element, and so on, and to minimize damage due to noise, vibration, dust, air pollution, water pollution, and soil contamination. And in use phase, when a work not established in the design phase is to be carried out in the maintenance and remedial activities, a work plan shall be formulated and the environmental impact generated from the work plan shall be calculated. And in use phase, consideration shall be given to, for instance, the environmental impact of substitute facilities, equipment, rain, such stoppage and traffic congestion due to repair of road structures, and operational energy, including heating and cooling, shall be included. So if the concrete can contribute to the energy reduction in the building, it should be considered. At the end phase, when demolishing concrete structures, demolition shall be carried out so that the demolition work should cause no harm to the neighboring community, and the arrangement of the resulting waste materials should not harm for the recycling work. And concrete demolition materials shall be recycled by methods that do not require excessive energy and do not generate large amount of waste without causing harm to the neighboring community due to noise, vibration, and dust. Is given in the part 1. And also in part 1, the result of the environmental impact assessment for concrete and concrete structures can be used for environmental rather than the environmental declaration. Very simple statement in part 1, and in part 8, which will be served in some years later, more detailed requirement is given in part 8. The next is part 2. This part 2 specifies the system boundary and the inventory data, which is very important to make a life cycle assessment of concrete and construction in the design phase and also in the production phase, distribution phase, and in each phase. So this is the table of the contents. We have 2 chapters, mainly the system boundary and the inventory data. In each chapter has the similar structure. The constraint concrete production and execution of concrete structures and use of concrete structures and end phase. In each phase, this standard specifies how to make a boundary and how to correct the inventory data in each stage. This shows the schematic of the system boundary and the inventory data. This is the system boundary which should be considered in each phase and whole life cycle of the concrete structure. The inventory data has two categories. One is input of the materials and energy and resources, which should be collected and counted, and another is the output from the boundary. It includes the product also, waste, substantive environmental impact. In this part 2, now we are discussing the finalization of this standard based on the comment from several countries. This is the definition of system boundary, data collection boundary, life cycle inventory analysis, inventory data, input and output. So in general, of system boundary, when conducting a life cycle assessment of concrete or concrete structures, the system boundary shall be demarcated. This is a very essential requirement. And for comparison among multiple alternatives, the system boundary shall be the same for all alternatives. This is very important to compare several projects, several technologies. For system boundary demarcation, the life cycle stages and the geographical system ranges to consider should be appropriately defined. But it is not necessary in principle to include the system boundary, the system environmental impact related to the production of equipment machinery necessary for the production of concrete or construction. So we don't care about the environmental impact generated in the production of equipment machinery. And also the activities indirectly related to the production of each material or the construction of concrete structures, such as sales administration, it is very small, may have to be included in the system boundary. But we can neglect this amount. For example, for the system boundary of the cement, you can see here the system boundary for the production of cement shall include the following. You can see here the transportation of fuel byproduct, waste derived fuel, and also the process of additional treatment byproduct used for the production of clinker, process of additional treatment waste derived fuel for the production of clinker, transportation of cement from cement plant to supply station. But we are discussing about the system boundary, that the system boundary for the production of cement shall not include transportation of cement from supply station or cement plant to the place of use. So the main discussion of the system boundary now is in the transportation of the waste and byproduct and product. So you can see here, this is the present result of the discussion. This is the system boundary of the cement production, but you can see here the blue line. This is the data collection boundary inside the system boundary. So the data collection boundary means the cement company shall collect the inventory data by themselves. outside the data collection boundary, for example, electricity and fuel, to produce this energy, they can use the inventory data supplied by these companies. So the main discussion is the transportation of the waste and byproduct. You can see here, the factory A produces a product for the materials, for the product. This product is used for the materials for the final product, which is produced in factory C. Product is transported from factory A to C. So this transportation, the system boundary of factory C should include or not, because transportation generate the carbon dioxide emission. Or this transportation should be included in the factory C. Now our solution, our answer is now this transportation should be included in the boundary of factory C. But the factory B generate the waste. But the waste is used for the materials for the final product in factory C. For example, the cement company utilize the fly ash for the raw material of cement later. In that case, the transportation is included in the system boundary in factory C or not. So this is the answer from our discussion now. This transportation should not be included in our boundary of factory C. So it depends on the material is a product or waste. Okay, so the next chapter is the inventory data. In general, inventory data include the following: the data on the types and the amount of the resource, energy, materials, component input into the system boundary, and also the output from the boundary. You can see here. And inventory data shall be objective, transparent, and reproducible. In order to accurately acquire the calculate such inventory data, it is desirable to conduct actual condition survey and trial experiment. But unit-based inventory data acquired and calculated in the past under the same condition, these data may be utilized if available. But in the case, reliable unit-based inventory data may be this should be shown in writing. The company show they utilize the inventory data, which is supplied by some reference. Yeah, the means, condition, and the information sources of the acquisition of inventory data and the calculation of unit-based inventory data shall be expressly indicated in the writing. and some other statement is in the general COVID-19. For example, in the cement, we divided the inventory data into the categorized into the direct input, indirect input, and direct output, and indirect output. And part 3 is for the constituent and concrete production. This is under investigation. The table of contents is here. This chapter shows how to reduce the environmental impact in the production of the constituent materials of concrete and also the production of the concrete. Part 4 is for the environmental design of concrete structures. This is under preparation. Maybe next year we will establish a working group in ISO SC8. This is the basic flow of environmental design. First, we need a client brief. Based on client brief, the performance of the environment is required, which is also based on the laws and the regulations. And we estimate the performance of the structure. And we can compare the requirement and the retained performance. If it's satisfied, the documentation is given. This is the table of contents. It includes the LCMS, how to calculate the life cycle inventory in the design stage. Next one is chapter 7. This is also under investigation for the end of life phase, including the recycling of concrete structures. This is the table of content. In this part 7, demolition work, intermediate treatment work, final disposal is 3 targets. In these chapters, how to reduce environmental impact are specified. The final one is chapter 8, part 8, labels and declaration. This will be established after establishment of the working group. Maybe I hope the South Korea will become a convener of this working group. This is the table of contents. After the life cycle assessment, the product, concrete product, and cement constituent material, they will show us how much environmental impact is embodied in such product based on this ISO standard. Okay. This and for my presentation.
Thank you. Unfortunately, we don't have time for questions, so thank you very much for your presentation. So we have the next speaker, Ms. Julie Buffenberger. She's chair of the Asia Commission 130, and her today's title, what are PCRs and EPDs?
Excellent. We were kind enough to hear a little bit about EPDs from Dr. Mueller. And obviously with ISO and the standards and the regulations that are being done, we were actually privy to see a little bit of the work that's been done behind the scenes by our ISO organization, obviously from Dr. Sakai and also Dr. Noguchi. So what are PCRs and EPDs? We're hearing these more and more in North America, but they are obviously not something that are new. seeing many come out of Europe. And there were some questions earlier today that hopefully I can answer in some of this presentation. But to kind of give you a little bit of indication what I'm going to speak about, I'm going to talk a little bit about the green construction market and how it's evolved and why we're where we're at and why we're hearing these new terms, EPDs and PCRs. And what are the drivers for getting us to this location? And certainly understanding what an EPD is, and finally realizing the development of these product category rules and what we're seeing right now in North America. Certainly if we look at green construction growth, it's nothing new for many of us that have been working in sustainability for the last several years. It's grown to almost 71 billion in 2010, and its growth potential is going to be about 145 billion in 2015. We can see that there are labels, and obviously they across all boundaries, all continents. There's about 495 labels today that we can point to all across the world. And so you can see that when you see all these differential factors and all these different rating systems and these versions to have sustainability or greenness attached to them, we have to come to some common definitions or some common science. If we look at North America, we're really looking at these specific standards. And it's really LEED, it's also Architecture 2030, Green Roads, the International Green Construction Code, Invest, Envision. All of these are really leading in different sectors. But it comes down to, again, is what can we find that is common across all these different rating systems? Certainly the USGBC and the LEED rating system are the most dominant that we see in North America, and they are really on the horizon throughout all the countries across the world. I receive questions from Croatia. I see questions from Singapore. We're starting to see the emergence of LEED and versions thereof in different countries. But it still remains as the most popular and most adopted rating system here in North America. And certainly if we can see its influence, we see that almost 7 billion square feet are in the pipeline today for new buildings that will be under the guise of the LEED rating system. Now certainly when I said there's other types of rating systems, these are for buildings only, but certainly we have things that do cover our roadways. And when we look at how the rating systems have evolved, we've seen different versions come and go. And now the version that we see before us in green buildings is looking at LEED version 4. And what we've seen is, again, a change or a growth or a maturation process that we see in these iterations of LEED. We've seen more increased technical stringency, looking at more operational impacts as we would see in some of the ISO and how they're looking at what about transportation, what about CO2, what about acidification of waters. Certainly it's become much more important than what it was. So measurement and reporting have begun to change. When we look at one of the credits, and this is just one of the new version of USGBC, it's looking at building product disclosure and optimization, environmental product declarations, also known as EPDs. Now what's important about this is that we look at these, and now for the first time we're asking for more transparency and, more importantly, third-party verification. So we're looking at EPDs, we're looking at where is the source of your raw materials, and certainly what are the material ingredients and how they play into the over environmental impacts. How does this change? This has changed because when we first started looking at LEED and other rating systems, it was simply about not scientifically based information, but there were labels attached. There was a type 1, and we see that, which was something about it's all natural. But we can't prove that it's all natural. We just know that they call it all natural. In the last version of LEED, in LEED 2000, 2.1, 2.2, and version 2009, we looked at something called a Type 2 declaration. And that declaration was really ISO 14021. It was a self-declaration. The problem was is that as we have become more familiar with sustainability, we've seen that manufacturers can look at their products and kind of maybe not make such scientific statements about them, but that was looked at as greenwashing. So our next step is to move ahead in the sequence and become more technical and more transparent. So so that we can look at a product and look and see how sustainable is it, or more so, what are its environmental impacts. And certainly that's where we become in ISO 14025, looking at what I will call a type 3 type of eco-label. And this is, we kind of look to it now in the industry as the nutrition label, or an actual label where we're quantifying scientifically based on some of the ISO boundary situations. If we look at an EPD, the main characteristics that we look at, it's credible, and it must be third-party validated. So some of the greenwashing that we saw is going to go away, which is good for designers and also good when we start looking in depth at what the impacts are. And certainly it's a consensus base. So when we look at how we get to the end point of an EPD, it was developed over time by a group of people and not just one individual group. So we have to have some comparability, and also it's voluntary today. But version 4 will mandate it now. So we're seeing changes, not only here, but in other types of documents, such as your IGCC documents. The big point here is that we have focused far too long in sustainability about greenhouse gases. It's not just about carbon dioxide. It's not about just CO2. Because I can guarantee you, if I'm over in Europe or if I'm in Africa, what they're concerned about are two totally different things. In Africa, they may be concerned more about the water and how the water is being impacted versus the amount of CO2 that's being produced. So when we look at the evolution of project design, we've really gone from looking at just materials and if they're recyclable, to now looking at materials, their operations, and the end of life. So an LCA, or a life cycle assessment, is really looking at a whole picture rather than just one little snapshot, which is important to us. And so an EPD is replacing what I would call that type 2 label, which is an environmentally preferred product, but not necessarily scientifically based in statements that are made if it's environmentally preferred or not. So when we look at, as I said, some of the selected environmental, and we also see economic indicators when we start looking at things like green roads, we can start now really deciding on our project what is best. And certainly Dr. Mueller pointed that out. You know, what is best for that specific project, that service life, and then we all have to say it comes down to money too. How do we balance all three, which is really when we talk about sustainability, economics, the environment, and the social impacts. So certainly here are some of the items that are on the list. We can look at total primary energy or embodied energy. We can look at water consumption. And certainly if we look at the sustainability of construction works, in Europe, the CEN-TC 350, everything in about the top 7 or 8 are in that type of document for sustainability. When we look at LEED version 4, we're really looking at greenhouse gas effects, photochemical ozone formation, depletion of non-renewable energy resources, and then you can also choose some other things like human toxicity is now going to be of concern because of health product declarations. But we're not here to talk about all these things. We're really talking about EPDs. So who is behind this change and why we're starting to look at environmental product declarations? Well, certainly I think one of the main drivers here has been Architecture 2030. And we've also seen the USGBC and their change from what I would call less technical guidelines to more scientifically based guidelines. They heard the people out there that said, we like your ideas, but there's no science behind them. So why are we comparing apples to oranges? When we look at a science-based approach, now we can really compare oranges to oranges. And certainly we look at the IGC and their construction code, and we've seen lots of local and state incentives. But really the main driver is Architecture 2030. And it's really been adopted by 70 of the top 100 architects. Now when I talk about architects, we're not talking just about North American architects, because as the world has more telecommunication, more ability to communicate, most of the architects are working on worldwide projects. So it's not just about North America, it's really a worldwide change. So certainly we're looking at the reduction of greenhouse gases and their impact on building operations and materials, and finally getting to that net zero. As Dr. Barsalov said, the population is growing. We still need more cement, but we have to get there somehow, some way. And when we start looking at products and how we can choose our products, we must start choosing wisely. When we look at the planning systems today, we have existing buildings, and they need to be retrofitted. How do we retrofit so that we're more sustainable? That's captured in 2030. And there are districts now throughout the United States, and we actually see cities across the world that have adopted more planning stages. I kind of look at this as a response to two things, sustainability, and now looking at what I would say climate adaptation. Because when we start to look at climate adaptation, it's not just about the materials. It's about specifics for your region. So it could be water. It could be CO2. It could be renewable energies. So Architecture 2030 and Architecture 2030 planning, it's really a worldwide acceptance criteria today. So we look at the challenges for buildings, and we heard a little bit about what if I change my structure and it's an ICF structure? We need to go to carbon neutral. We need to go further. So now we have to look at how we can impact that. Certainly we look at a challenge for products. So now if we look at this, we've gone from the building now down to the products. How can we quantify the impacts of those products? We can't really quantify if we just say, I believe it's sustainable and it's got 20% recycled content in it. It's really not talking about environmental impacts on the overall usage of that building or the use phase of that building. So certainly we have to do this better. As I said, what are the stakeholders? The top firms that are working around the world, not the top firms just in North America. They're around the world. We look at ARA, ACOM, URS, Jacobs, Bechtel. All of them are working on worldwide projects. If we were at the international luncheon tomorrow, we would hear about the Panama Canal. Again, worldwide engineering systems that are being looked at. And not only that, we have contractors, Turner, Gilbane, the big names that we have heard from around the world are all now looking at how can we scientifically capture and how can we account for what we do in buildings. So when we look at sustainability, we still see ASTM. And ASTM, again, has announced that their intent is to look at PCRs and study PCRs and EPDs, but more so they're going to become a program operator so that they can help quantify for others in the industry what the environmental impacts are through environmental product groups. So what are PCRs and EPDs? An EPD is an environmental product declaration based on a couple of things. You have a life cycle assessment, which we heard about from Dr. Noguchi, who were looking at the process. How are things manufactured? What is the process in manufacture? What is the end of life of that product? We also must look into this product category rules, which I'll describe a little bit more. And finally, we have to have data behind this, some scientific data that has been gathered through system boundaries. And it can be inventory data, or it can be very plant specific. So if we go back to our nutrition label and we affiliate it with concrete, we might be looking at new types of impact categories, which I think Dawn asked about earlier. You know, where did you come up with these categories? How were they founded? Well, they really come out of the ISO standards. And so we look at things like acidification, ozone depletion, global warming potential. CO2 is still there, but now we have other items to look at. So certainly when we look at an EPD, it's really translating that life cycle assessment data into environmental impacts. And certainly we can, it follows, as I said, the ISO criteria. Now what's important about an EPD or to understand an EPD is that you can use an industry EPD, which we're seeing right now in North America. You can use a company EPD, which we see more about product specific, where we may see a company that goes ahead and does their own and develops their own EPDs. And that they can be specific to a certain plant even. So again, it can become much more detailed and as detailed as you'd like it to be. EPDs are viewed and updated every 3 years. So again, this is a work in progress. just as we've seen more technical stringency, we're going to have to see an update of data because we know processes change. The way we manufacture changes. So when we see new cements and we see new products, their impacts have perhaps changed, and we need to account for those. So if we look at life cycle assessment again, I'm not going to go through this in detail because obviously Dr. Noguchi did a very nice job, but we can look at the part of the management standard and say, okay, if I'm making concrete, what am I concerned about? I'm certainly concerned about the cement, the aggregate, and the water, the materials that comprise concrete. I have to be concerned about the transport. Then I have to worry about the transportation of the concrete from the plant or if it's on location to the project. And then the construction of that project. What type of construction is impacting that project? Am I using diesel trucks on that project or am I using natural gas trucks on that project? How does that transportation impact? What are the environmental impacts? Certainly we have construction, then we have the use of that building with concrete, and certainly recycling. So what are our paths to get to our EPD? First, we have product category rules. And again, these are based on ISO 14024. We must conduct an LCA of manufacture. Then we must verify the LCA. We draft an environmental product declaration. We can validate the EPD, and then we must register the EPD. So it is a process. Now, how do we get there? As I said, product category rules. When we look at a product category rule, it is written so that all of the, let's say, steel, all steels would follow under the same product category rule. So we are comparing apples to apples. You don't compare a product category rule for steel versus concrete. They are written specifically for a product. You have a functional unit. In this case for concrete, we are going to base our product category rules off of 1 cubic yard or 1 cubic meter of concrete. We have system boundaries. What are we going to include? The pre-use, the use, and the end of life. What are the impacts? What are we going to report? Certainly, then we must register the PCR, and this is done through a program operator, and as we saw, that ASTM is going to become a program operator. There are other program operators such as NRMCA. There are varied program operators. PCRs are effective for 5 years unless there's a change in the life cycle assessment and methodology. So again, we're comparing apples to apples, 1 cubic yard of concrete versus 1 cubic yard of concrete. We're not comparing concrete versus steel. So they're separate. So how do we make the EPD then? How do we go forward? Just like when we looked at LEED and we said this concrete is an assembly of materials. We must now additively look at all the EPDs that go into concrete. So you would have the admixtures. You would have the EPD for aggregate. You would have the EPD for slag cement, for fly ash, for cement. These all go into this product that we call concrete. And then you would take all the EPDs from all the different products that are used in the building, and we would collectively put them together to create the whole building life cycle assessment. So can we do this for concrete? Everyone finds this quite frightening. We have thousands of mixed designs. What are we going to do? We have a new mixed design developed for every single project. How are we going to account for that? Yes, it's going to be difficult, but it's not doable. So we have to look at upstream data. We can look at averages. The PCR for concrete has been developed by the Carbon Leadership Forum, but it is being reviewed and revised under ASTM at this point. If we look at the state of the industry of the PCRs that we are concerned about, concrete, cement, slag, and fly ash are all in different, I would say, steps for the PCR. All of these, you note, are industry PCRs at this time. There's only one company that has an EPD out at this point. So the PCRs have to be developed really before we can make the new EPDs. So again, if we go back to, we have to, when we look at the PCR, what is the declared unit? In this case, it's 1 meter or 1 cubic yard of concrete. What's required? We need to know what is going to be the specified compressive strength at the age. So it's either 30 MPa at 28 days, or what is the MPa of that concrete? Because again, if I'm choosing concrete from producer A and concrete from producer B, I can't look at 6,500 PSI concrete versus 4,000 PSI concrete. They're different. So I have to look at them equivocally across the board. Optionally, you can look at exposure class. We could look at some design criteria or other performance criteria. We're going to have to look at the life cycle stages. So again, raw material supply, what is the transport? Look at manufacturing, the construction process. We can look at transportation. These are all the things that are going to feed into our final LCA. We have system boundaries. And again, these, you have to look at aggregates. Are they crushed aggregates? Are they cement? Is it water? Is it admixtures? All of these are detailed when we look at a concrete PCR and a concrete EPD. So impacts that need to be reported, these are based on, again, ISO, the boundaries. We're going to be looking at climate change or carbon footprint, our ozone depletion, acidification, eutrophication, photochemical ozone or smog, and all of these are under the TRACY, which is the Tool for Reduction Assessment of Chemical and Other Environmental Impacts. Some life cycle data that can be reported as well is primary energy, total water consumption, looking at the concrete batch water, hazardous waste, what is your use of primary energy, carbon emissions from biofuel. So everything that we've talked about in the sustainability world and the impacts that we might see are really viewed quite scientifically when we start looking at PCRs and EPDs. So a selection of data. Again, are we going to be down to be very plant specific? Are we going to use company weighted averages? Can we use a regional weighted average? We have to be ISO compliant, and we have to make sure that the life cycle inventory data, which is basically the data that everyone is giving for the input, is reviewed. Certainly we need to look at the default LCI sources, and these right now in the PCR for concrete are being included in Appendix B, and again, ASTM is reviewing this. Other sources, but not limited to, there's other data sets. There's a lot of data that really does exist out there. The issue is getting to it. So in our case, I look at, say, the cement industry. The cement industry is sharing data. Some of the data is available from a worldwide basis, but now we're looking at an industry EPD or an industry PCR. So Central Concrete actually went ahead and looked at their specific plant. And this was done out in California. Now, this was done for a specific project. I'm not going to lie to you. Google's building a new complex, and Central Concrete knows Google, likes to be ahead of the game. Google wants to be as green as possible. So they are looking at having an EPD in place for the concrete that's going to be used on this project and on their complex. They also look at health product declarations. So in order to be awarded this job, Central Concrete went ahead and said, okay, I need to look at our mix designs, and I need to make sure my mix designs have EPDs affiliated with them. They had 1,479 mixes that were looked at. And the things that they looked at, again, were 28-day compressive strength. They looked at total primary energy consumption, batch water, wash water, global warming potential, ozone depletion, acidification, eutrophication, and photochemical ozone creation, which is small. So when we look at their document, it starts out that it's EPD. It's talking about service areas that are covered. So this is actually looking at 1, 2, 3, 4, 5, 6, 7, 8 plants. And you go on to the next page. It's a declared product. Program operator, so who was the person that helped them put the PCR together? That was NRMCA. Who is the LCA developer and EPD developer? shows it was Climate Earth. Who was the independent verifier? Again, so you have verification by one group, but then it must be actually third-party review too. So they had a third-party review from Athena, and then they talk about the product category rule and then the date of issuance. They have product description, the declared unit, the life cycle assessment, a summary, and again a summary of the limitations of the EPD. So there are limitations obviously that we need to be aware of. So some of those limitations are life cycle impact, assessment results are relative expression. So they're saying they're data, but there is some boundary conditions related to them. Certainly if we look at Portland, they describe the products that are comprising and where they might have received that particular EPD that rolls up into concrete. So they have Portland cement, fly ash, slag cement. And again, because these PCRs and EPDs were not developed yet in the United States, you can see that they actually used the EPD from Switzerland because it's the best one that they had to use at the time. Now there are little differences between the European system and the North American system, but it's the best they had. So they went ahead and used these. And again, accelerating admixtures, they're looking at their admixtures, and again, the geography from the EPD they used was Europe, because North America is still in the developmental stage of some of the EPDs. Yes, thank you. All right, environmental impacts, I'm almost done here. Appendix, again, they're mixed designs. You can see they came out, and they list all the types. So the data will be needed for the LCA, the materials that are used over 1 year, the distance to the material supplier, the energy, water use, and mixed designs. And again, going through the system is you search for the PCRs, or a new PCR must be created. You conduct and verify an LCA. It's verification, registration. So everything has a very nice order to it. So here are some independent reviewers for EPDs. Athena Institute, Carbon Sense Solutions. There's numerous groups. So I'm not telling you to use any one of these groups, but certainly there's several. I just wanted to put a little price tag up here. This is from the NRMCA. I have no way promoting them, but I wanted to give you a flavor of the cost. There is level 1 verification, level 2 verification, and then you get a discount if you're a member of NRMCA. But certainly EPD documents are not solely alone just for the concrete industry. They're covering all sorts of our competitors as well. And certainly, as I said, you can use existing PCRs. This is one that was done for reinforcing steel. But where I see the future going, again, we have to look at the future, is when we can start to marry environmental product declarations with new tools like BIM, accounting becomes very easy to look at the impacts on the overall part of the building or of your structure, whether it's a road, whether it's a bridge, whether it's a building. We can start to see now, even within ACI, we have a new group that looks at BIM and how concrete blends into BIM and how construction leads into BIM. And certainly I believe this is part of it. So EPDs are here. They establish relevant boundaries. There's industry averages that can be used, but certainly I see this as a step forward in more stringent requirements and more scientifically based ideas when we look at environmental impacts. So with that, I thank you for your time, and I don't know if we have time for questions, Koji.
I don't think so. Okay, we have the last speaker, Professor Dong Choi from Korea. He is a chair of the KCI Green Committee for Concrete. The title of his presentation today is Recent Advances in Standardization on Sustainability in Korea.
Yes, I'm very honored to be here to discuss our situation on development of environmental standard on concrete in Korea. My discussion, I think you will find that my presentation is in line with Dr. Noguchi's and Julie's in terms of environmental standard, more so toward the later part of my discussion.
Korea is not a very large country, as you know, but we are about greenhouse gas emitting country, and the rate of increase is very fast. So this matters to us. As you can see in the lower, it's almost the same as 10, and is lower than our reference. Perhaps because we are not very large, we are taking some special responsibility government-wise. It's called the target management, and Dr. Barcello mentioned about sectoral approach earlier today, and I think it's in line with the sectoral approach. So government dedicates some 480 business enterprises. We call them controlled entities, and they altogether emit more than 60% of all greenhouse gases in Korea. So we assign targets to these controlled entities, and they perform and submit performance report, and we do it annually. Cement production, again, we are about 2% share of the world cement production, and nationally cement production is about 6% of all greenhouse gas production. Our cement production is consists in a similar way to that of Japan, type 1, 75%, about 20% blended cement. And Korea Cement Industrial Association, they formed 6 strategies to cut down their CO2 emission by 8.5% by 2020. The most important one is cementitious substitution by new cement standard, which will allow up to 10% SCM. But I know that U.S. has already established this kind of standard, and we are following the same path. We want to increase the usage of blended cement up to 28% by 2020. Currently is 20%. And the other 4 strategies will contribute, but not as much as the first 2. New cement standard on the Portland limestone cement. Again, I know Canada has already launched this kind of standard, and we are trying to follow the example of Canada and some other countries which has already done this. We try to complete this draft by January next year. I was the driving force pretty much behind this one. The Architectural Institute of Korea, we have recently revised their construction standard specification, and we are now requiring the constructor to submit environmental management plan for construction before the construction begins. There are 2 passes, mandatory and optional, and mandatory pass includes the increased use of reused recycled amount and C&D waste, and environmental management on site. Optional pass includes greenhouse gas emission, reduction of the use of natural resources, and water management. This is should be done in practice in Korea now. I want to give 2 specific research case study results briefly. First one is called CO2-based SCM design. This is similar to what Professor Mueller presented earlier today. About 4,000 mixed data have been gathered by a research team, and we wanted to analyze this in terms of so-called CO2 index, which is CO2 emission divided by concrete strength. So it's emission per unit strength. So as you can see on the right-hand side, the figure, we grouped those mixed designs into to 6 categories and perform some statistical analysis, and the result is the same as the one shown by Dr. Mueller. CI decreased with increasing progressive strength, and this tendency is more pronounced with a normal strength score. Very useful conclusion for us. And then we did more multiple regression analysis, and the result is this one as an example. We call this CO2-based SCM design chart, and it can be used as follows. If I use 30% fly ash on the x-axis, and then I go up to the second line, for example, I use 20% blast furnace slag, and on the y-axis it shows that I have reduced 25% CO2 when I compare it to ordinary Portland cement. And this is shown by equation 1, as you can see here. And as you can see, this kind of diagram we are trying to incorporate in our concrete standard specification. We are investigating the possibility. Second research that I want to discuss briefly is LCA of fine aggregate production. I know that many similar studies have been done, but the result has not been very publicly. Yeah, as we have expected, environmental impact of crushed natural aggregate was the highest among all natural aggregate. You can see in terms of use of energy and greenhouse gas emission. But perhaps more importantly, environmental impact of recycled aggregate production was really huge. I don't want to disclose a specific number here because it's just a result of one study, but it was really significant, and we should discuss in the future about what we can do about this. Now I want to come back to this issue of stand-up, which is the main subject of my presentation today. In Korea, the greenhouse gas emission is mainly controlled by government, as I first stated. So greenhouse gas guideline in general, and guideline for cement industry, guideline for such and such, controlled on the target management. Institutional effort continues, as I said also earlier, Architectural Institute of Korea specification. We are also working on the environmental specification part of KCI standard specification and similar works in Korean Society of Civil Engineers. And on the other hand, we have adopted ISO standard on LCA and EPD for general industrial products. For concrete, what we do is what is shown in the large rectangular box. For about 10 years, we have been developing LCI database, and we have two kinds, KLCI-DB and APSS. The latter is more construction-oriented, and we have altogether developed 700 or 800 database, which took That's a lot of time and money. But anyway, more LCI data are being developed. In the middle column, there are EPD of cement, EPD of aggregate, EPD of ready-mix concrete, are all the Korean standard where the final draft has been completed but not yet launched. It's very difficult to launch these kind of standard in fact. But anyway, we are continuing our effort as I in the next slide. Of course, we have a standard recycling rate. This is a situation in a standard organization. Dr. Noguchi already mentioned briefly. We have ISO 15392 and ISO 21929-1, which covers all three sustainability aspects of environment, economic, and social. ISO 21930 is the main one for the EPD of a building product, and many countries are following examples of ISO 21930. In my opinion, and I think others also agree, the ISO 21931-1 is the one for the framework for method assessment for the environmental performance of construction. That should be the main target of this standardization. When I compare this international situation to Korean situation, the situation is as shown in the screen. We don't have any standard yet for the general methodological basic, which covers all three axes of sustainability. But we have adapted ISO 21930 as Korean standard. We have also adapted 21931-1 as KS ISO. Yeah. At the same time, as Dr. Noguchi already told, the effort of TC71, which is the 13315 series, we are already trying to adopt this as ISO in Korean standard. I find that a box is missing, as shown on the right lower-hand side. Environmental declaration for concrete, like as said in the previous discussion. So this is the life cycle of concrete that we have worked so far. It consists of 4 phases. Phase 1 for production of concrete constituent and the production of concrete. Phase 2, execution or construction of structures. Reuse of concrete structures for end of life. And we think that we need 14 information modules. 5 for concrete constituent, 2 for the concrete production, 2 for construction, 2 and 3 for the other phases as shown. It can be declared as one aggregated information module, items 1 through 5, or it can be declared in 3 different parts: raw material acquisition, transportation, and production. And as we know that we need the scenarios for the construction and the related part. Also, there will be some cradle to gate and cradle to grave options. The last one is very difficult to meet. So why we have to do this? What will be the objectives of the EPD for concrete? So we have defined 4. Is to provide the environmental information to be used as performance criterion for concrete, and to facilitate communication of the environmental information involved within the life cycle of concrete, and to enable producers of concrete to reduce environmental impact. This will be the direct target. And the last one, to enable designers or constructors to reduce environmental impact on concrete structures. I think this is a more long-term target which will be more complete with some kind of new concept like environmental design, as Professor Noguchi mentioned. Yeah, this may be the last slide, but without about the conclusion. KCI and we have developed this type 3 equation of cement, aggregate, and ready-mix concrete, and also we are working on concrete. Oh, one more thing. Yeah, as I said, we have spent about 10 years to develop this ACI database. I think it's very difficult, very costly, very time-consuming. Julie already mentioned that in her example EPD, the specific company accepted ACI database from Swiss. Even though when US is doing that, ACI database is actually a national database. How many nations can develop ACI database? It's very, very questionable. If a nation or a nation cannot develop database, they may not be able to perform ACI. So, in practice, it's not very easy, technical-wise, economically, to do ACA. Yeah, in practice. Okay, I will conclude with a few remarks. In general, we find that adoption of new sustainable technologies is not easy. Our new cement standard, the public hearing has been going on for more than 1 year. It's not very typical for Korea. But effort at institutional and governmental level continues. As I have shown with two example cases, we should be able to expect what kind of CO2 amount, reduction amount can be achieved at the design stage, and we need technology for that. And I have shown an example. And I think we need to work on environmental impact categories. I have asked the question to Professor Miller already. He used something called the eco-balance. Yeah, it's not ISO, I know. Julie already mentioned EPD, the newest version. It includes 4 mandatory categories. Yeah, it's been agreed in the US, I understand. But will that be the same in other countries? Or will that be internationally agreed? I think we need more sound scientific proof or result of research in that area. A good example, I think, is CML performed by Leiden University in Europe. But that is for the building construction in general. So we need research, similar research in concrete area, I think. Okay, standardization, of course, the environmental standardization in concrete industry should continue. And yeah, I'd like to say, as we should do, and we are doing in Korea, this kind of standardization should be in harmony with international effort, such as those being done by TC59 and TC71, both the chairman of TC71. I'd like to conclude my presentation. Thank you.
Thank you. I think that he can have the one question because now he showed this presentation. Is there any comment or question to the activity in Korea? If not, I think that we can discuss later on together. Thank you all speakers. I think that we will continue the panel discussion. The time is only 20 minutes, so
It's very hard as far as like durability, because if you have potentially 5 to 8 different components that go in that mixture, you might things like solutions and ester. You can probably weigh them, and you could put them here, but I think it's very difficult if we look at it across. Actually, we have a comment that came in from the internet. It says, I think that there are an important number of studies about absolute SEM, but it doesn't take into consideration the influence of the land change by product exploitation or consumption, cement and aggregates on climate change. You know, there are things that are not taken into consideration into the PCRs or the EPDs because, again, they're product specific, whether we like that or not. But I think as we move forward, that more of these items are being taken into consideration, and I do think that when we see changes in land mass, or we see
all of the EPDs, PCRs, the ISO standards, what I saw was a lot of negatives, negative impacts. And I think one thing that we have to keep in perspective, Laura mentioned that there's 15 billion tons of concrete used, and those are used for hospitals and schools and water treatment plants and water delivery systems, and a lot of positives for society. And I think a way to quantify that is the real way to balance your impacts. A large intersection down in Texas used a lot of concrete, but it was a non-attainment air quality area. And now the air quality has improved. So how do you balance that up when we're talking about that? So I think that's something we could look at, is how to balance not only, you know, getting the glass a quarter full, but saying that it really is full from a positive perspective.
Totally agree. So the other comment? I think that the move to the second, what is the key to accelerate self-life design for sustainable concrete structure? Professor Mura talked about this, but it seems to me a bit difficult to apply this idea in practice. So what is the point to accelerate this idea? Maybe you can comment first.
So I'm really convinced that our way of design is wrong. It is simple, it is practical, but it is wrong. And but the next step I try to present is very complicated, very sophisticated. It's a little bit too elaborated. So we must find a compromise between. I think we can do much more if we define exactly the planned service life of our structures. So if you look to reality, we plan for the time being bridges for 80 years. Most of our bridges, the ones that have 100, 150 years or more. If we are planning tunnels in Europe, we have large tunnel projects. We have now a planning for 200 years because they are so cost intensive that our economy will not be able to replace them within 30 or 50 years. So in these cases, we must use other tools for design than those we have used up to now. And this is the way for service life design. though it is a little bit too elaborated, but I think the way is the right one. We have to find a simplified compromise.
Okay, thank you. That's probably that the direction which we have to pursue should be clarified for the future, even if currently it's difficult. That's what you're thinking. Is there any comment on the sub-staff design? A bit difficult. And maybe Julie may comment on that. What are the essential benefits to introduce EPD in concrete industry? You have already mentioned some, but additional.
I think the largest part is that you're now able to compare or make a comparison of things equally. Where in the past that you had to go on maybe not so scientific criteria. It was maybe based on quality control, or it was based on delivery time, or there were maybe some other underlying factors. With that said, however, there is things like quality. There are things such as other items that will lead you to, say, one producer over another producer. I think the point is that at least we have some science behind some of the declarations that we were making about concrete. But I would agree again back with Barry that while it's all scientifically based, it really doesn't take into some of the considerations when you talk about society or the, as I would say, the softer side of sustainability when we look at social impacts. So yes, we have more of the science and the environmentalism that we found with EPDs, but I think what's lost on us still, and that's why I always like to keep EPDs in perspective, is that when we talk about sustainability, we also must look at the three-legged stool, and that even though concrete now can be quantified, we still don't look at the social aspects as much as we can, such as building a bridge now unites two villages that were not united before, or the other impacts where a hospital is still standing, or the resilient factors of concrete are not often taken into consideration. And I think that's what's lacking when we look solely and specifically at the science.
It's a question, and it's regarding the what Professor Muller mentioned during his presentation. But Julie, how do you think you are going to take into account the fact that in spite of having higher impacts, a high-performance concrete or a ultra-high-performance concrete may be more durable and for the life cycle of the building may be beneficial, but it will not show up in the EPD. So,
and I think that goes back to the whole idea that when we look at the total life cycle, and that's what's really not captured very well, because we have structures like the Pantheon that are still standing. So is its life cycle over? No. Can we quantify that yet? No. So I think it comes down to me personally looking at the resilient nature of structures and of concrete in itself. And at some things we've not repurposed those buildings as much as we could. And I think it's somewhat of a mentality that we have to get beyond, that yes, we have science, yes, we have good concrete. But it kind of comes back again to, have we really quantified the durability issues as well as we can? No, I do not think so. We've designed for 100 years. Well, why aren't we designing for 1,000 years? There are structures that have been designed for 1,000 years, specifically in towers and so forth across the world. Why are we, and this is where I kind of limit our imagination, speech comes into play. Designers were used to specifying or delivering a building to meet a specific use, and that was typically a 20-year building. And then we saw changes in codes because we wanted to make it more cost-effective. But we look at our building stock and we look at our building structures, and those that were built 50 years ago are far superior to what's been being built today, because changes in codes, changes in economy, changes what was important to us, which is typically or has been first cost. If we go back to more of a European thought, is I'm building this building for my family and they're going to live here for the number of generations that are going to be, that's a different mindset. So I think part of it is mindsets have to change of how we look at concrete and the value and how we value concrete. and its overall perception in how designers look at it or how entrepreneurs or building developers look at it is, it's often been said, what's the most sustainable building? The building that already stands that doesn't have to be rebuilt. And that's where the durability and the resilience and all those issues come into play that I would call them the softer side of concrete, but it's really the hard facts of concrete. You know, that's why it's the most consumed building material, because it has a life safety issue that is not quantifiable in all respects. But I would assume that people that have been through natural disasters, such as Japan or Haiti or some of the other countries around the world who have recently gone through these things, they will tell you that the person that is grateful for concrete is the one that was standing in the storm shelter and lived through the storm or the tsunami or whatever it was. And that's what's not captured yet.
Could you tell me about the mechanisms why the EPD is functioning in Germany? What is the mechanism?
Strong political reason. I cannot explain it, but it was introduced at the beginning of this year that every product, not only the building product, every product which is on the market must have an EPD, and there is an access at the Ministry of Economy where everybody in Germany can look for the EPD of the product which is on the market.
Is that regulation?
Okay.
Is that regulation? Regulation, law.
Law is a law, right? It's a law. It's a law. And I think it creates clear clarity. So, just coaching one point to a service life design that I forgot to mention. You save material and you avoid restoration work. This is two major points which are strong for service life design. May I ask just a question? It was a very nice overview you gave us on the EPDs, and just at the end you mentioned another system, BIM. What is BIM? Is it something like LED or?
Computer. Okay, let's move to the fourth one. Do you have any opinion on the development of the international environmental sustainability standard for concrete sector? So far, most of people pay attention to the ISO 14000 series for the energy. But as I mentioned that, we are now developing the environmental standard for concrete sector. Dr. Noguchi presented. Do you have any question on that or comment? If none, okay. The last question is what are the barriers to introduce new sustainable and resilient concrete in practice? Do you have any opinion? The people are making an effort to develop the new concrete, new type of the concrete, new type of cement. But
Koji, I'm actually going to add to that a comment that we received from the internet. And it says, sustainability is balance between life cycle and performance, but I think it will be more important to make balance between global warming and sustainability compounded with life cycle and performance, which when we kind of talked about the global warming potentials, it kind of comes down to this whole idea of climate mitigation, climate adaptation, and certainly resiliency. So if we kind of add that to the mix of the question, perhaps there are some comments.
Most proper person to answer this question.
So one thought on resiliency, I mean, I think it's key, but I think we are facing a major difficulty here. And the way I see it is we are already struggling to make people realize that they should not only consider the upfront cost of the structure, but also the use phase. And with the resiliency, we are going one step further. We are going to events that have a quite low probability to occur. So for the use phase, which has a 100% probability to occur, it's already difficult for people to take that into account when they are doing their buying decision or design decisions. So I think the key is to be able to really quantify in a probabilistic way what it means, and that's, I believe, the way to go.
Okay, I think that the time is up, so I'd like to conclude the panel discussion today. But let me make a comment, something. When we start this forum, the content of the speaker is not concrete. So the very conceptual. We are discussing very conceptual things. But gradually, we have had the new materials and new methodologies, and then the systems like ISO have been developed. So I think that we are now in a position to go to the next step from that point of view. So I'd like to conclude by saying this comment. Thank you for your participation.